In this video, we're going to talk about fitting and cross-validating other kinds of regression strategies in R. We'll begin by loading the tidyverse and updating the theme, and then we're going to load the tidymodels package. The tidymodels package, like the tidyverse, is going to be a meta package, but the tidymodels package is going to have several packages that deal with modeling and assessing different models. So it's a really clean, nice package to use for various modeling purposes. We'll then go ahead and generate a synthetic data set by setting the seed to be 5, the number of observations to be 21, our sigma, the standard deviation on the error term, to be 0.25, and then our true regression function to be this sinusoid. Okay, so we wouldn't be able to fit that with a polynomial exactly, but it'll give us some nice flexible data that we can consider as we model. We'll then make the data set by setting the x's to be a sequence between 0 and 1, and y equal to f of x plus some normal noise based on that standard deviation. The data is going to look like this. So it's just a sequence of x, y pairs, like in simple linear regression. From there, we're going to go ahead and visualize our data just so we can see what it looks like. So we have just a nice little scatter plot. We see this point pattern down here, so the function goes up and then down and kind of up and down again, but with quite a bit of noise there. And then we're going to make a new data set that's going to be used for predictions. We'll set the number of observations that we want to predict to be the same number as the number of observations in the data set. And the new data has exactly the same functional form, except for the x's are selected randomly between 0 and 1, with every point being equally likely. And if we plot them, they look like this. So this is actually a new data set, and then when we make predictions on it, we would make predictions only for the x's. So we would kind of forget that we have the y's. Now I'd like to begin this discussion with showing you how to use validation sets in R. So the idea here is that we're going to manually compute the residual sums of squares for several different models on a single validation set. Okay, so we'll go to our data set, we'll hold out a particular validation set, we'll train all of our models on the larger data set, that training data set, and then we'll apply them to the validation set and see how they do. So first, to make the training and validation sets, by the way, I may use the term test and validation set synonymously. They are actually a little bit different in practice. In practice, you would do this at the very beginning. So you would take your entire data set, hold out a test set, and then only work on the training set. And with the training set, you would further subdivide that into validation sets and so on. But I'll use those terms synonymously here. So to make the training and test data sets, I'm going to actually need to have what's called a split object. Split is initial split data, that's my data set, and then prop is 0.90. So I'm actually going to do a 90% 10% divide here between training and validation, very similar to what I would do in cross-validation, but with cross-validation I would do it several different times. Okay, this creates what's called a split object, and it's not very interesting to look at. 19, 2, and 21. Our data set has 21 observations. So to break it into 90% and 10%, we have to do a little bit of rounding. And the little bit of rounding that it did was 19 in the training set, 2 in the validation set, and then the total is 21 observations. Okay, so now we can break this up into data train. I'll call it data trn. That's going to be training split. And then the same thing for test, but I'll call that tst, and we call this testing. So training is this data set. Notice that it has 19 observations, and testing is over here. It of course only has 2 observations, and those were randomly drawn from the data set. They were randomly drawn to be 0.4, x is 0.4, and x is 1. Okay, so the one far on the boundary. So from here, it's useful to go ahead and make the number of the training data set in trn. So this is just in row data trn. The idea there is that the number of observations in a data set comes up very commonly in a lot of modeling tasks. So it's helpful at this point to just say, okay, well, how many observations are we actually going to be training on? Okay. Now the models that we're going to be comparing here are going to be polynomials of differing degrees. Okay. So we'll go ahead and we'll start by creating a degrees vector. I'll call it degs. Degs is 1 to n trn minus 1. So the highest possible degree for a polynomial that we would allow is n trn, so the number of training observations minus 1. You may remember that fact from the lecture, that if you have polynomials of degree n minus 1, they can perfectly interpolate data sets of n points. Okay, so this is what my degrees look like, nothing very special there. And now I'm going to make a vector for my residual sums of squares. and its length is going to be the same length. So length is n_trn minus 1. And of course, it just is a vector of falses right now. Once we put numbers in them, they'll start populating with residual sums of squares, because that's what we're going to want to put in it. Okay. Now, how do we want to actually go about doing this? Well, let's do it for one model first, and then we'll generalize it by putting it in a for loop. So to do it for one model, what do we want to do? We want to type in lm, so we want to fit a linear model y based on the x's, where the data is coming from the training data set, right? So data trn, just like this. But in general, this x here is not going to be x, it's going to be like a polynomial in x, and it's going to be of degree deg. Okay, so I'll go ahead, maybe I'll type in deg is 1, just so we can kind of like make this actually work. So there's a first degree polynomial. We could put in, by the way, raw equals true here, but I'm not actually interested in the coefficients at this time. I'm only interested in the residual sums of squares. Okay, so this is the model that I want. The model is going to be that model, and from there I want to use that model to make predictions on the testing set, that validation set that I've held out, right? So maybe I'll call those ypred, and that's going to be predict with model on the test data set. So data tst, and I should pull out only the x column, okay? In other words, when I go to that testing data set, we know that it has x's and y's, but I only want the x's. So I'll go ahead and say data test select x, so that will be my data frame, and then I can make my predictions. They look like this. That looks good. And now I have my ypred as a vector. Now, the only other thing that I need to do here is I'll need to compute my residual sums of squares, is that I need to compare the y's in data test to the predicted y's, right? So those would be, the actual y's are going to be data tst y, and then I just compare them using kind of the residual sums of squares criterion. So it's y minus ypred, and I need to square that, and then I need to sum that. There are only two of them, but that's the basic idea. And then this would be the RSS, right? That's the residual sums of squares here. And let me wrap this in a parentheses just so we can see it and make sure that it's working properly. Okay, everything looks good there. And this will do it for degree 1, okay? Because we typed in deg equals 1 before. Now I want to do it for all the degrees. So how can I do that? Well, I've already templated everything fine. So all I need to do is run a for loop through this. So for deg in degs, right? Each degree in degrees. I want to fit the model. Okay, that looks good. I want to make the predictions. That looks good. I want to pull the y out of the data set. That's going to be the same thing every time, but I guess I can put that in a for loop. And then I want to compute the residual sums of squares. Now, if I write it just like this, I'll overwrite RSS every time. That's why we have line 58 up here, is to create kind of like a container to hold those residual sums of squares. So I'll say RSS's deg is sum just like this, okay? So this should, if everything goes to plan, go through and compute all those residual sums of squares, and it looks like it does, which is great. So now what I'll do is I'll create a tibble that has in the first column the degree, that's degs, and in the second column the residual sums of squares, that's RSS is, like this. And this looks good. In fact, the nice formatting of the tibble here is actually very helpful because you can see exactly what's going on. So when the degree is low, the RSS is low, but as the degree increases, it gets kind of lower and lower and lower. Here at degree 6, it looks like it obtains a kind of minimum, and then it starts skyrocketing, so that as the higher degrees get seen, the error is worse and worse and worse. And we can go ahead and actually plot this if we want to. So we'll just pipe it into ggplot, es_degs, or deg rss, plus, we want this to be kind of like a line chart with a point layer on top of it. So geom line, just like that, plus geom point, and we'll see what this looks like. Okay, this looks good, but obviously the RSS of those bad models is like swamping everything. So what we'll do is we'll kind of come in here and we'll type in chord Cartesian ylem is, and now let's kind of get a reasonable range here. So 0 is of course going to be on the bottom end of that, and then maybe on the upper range. Well, let's see, it bounces from 0.109 to 182. So maybe we'll just put in something like 5 here and see what this looks like. So the curve, the residual sums of squares on the validation set gets worse, 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 and then it gets better, 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 and then it kind of is the same, and then just shoots off. So this chord Cartesian is just going to crop that image to some y range and not going to mess with things otherwise. Okay, we could play with this more. Obviously, if we ran this again, we would get something that could look very different, and the reason why it would look very different is it have a different validation set. Okay, so each time we run this, it's going to look different, and the reason why it looks so incredibly different with this particular scenario is that our data set is very small, right? The validation set only has 2 observations in it. So that is how we can do just kind of basic validation set stuff in R. If we want to go further, we can use the tidy models framework to have kind of a consistent modeling framework with which to understand models, to fit models. They're different than linear regression, and then to do things like cross-validation. So the major trade-off that we're going to need here with this is that our base syntax is going to change. So previously we would fit models that would look like this. LM y tilde x, data is data. And there's nothing wrong with that. That works just fine. The problem is that it's not very extensible. If we want to communicate a different model, like k-nearest neighbors or random forest, the syntax is going to look very different, okay? Or at least it could look different in general, and for those models, in fact, it does. So what the tidy models framework is going to do is it's going to express the same thing, but in a slightly different way. The first thing that you need to do is tell it what kind of a model you're using in general. In this case, it's linear regression. So this is coming from the parsnip package, and the mode is regression. Okay, linear regression can be used for regression or classification, and I always think it's a good idea kind of up front, if you can, to specify what kind of modeling you're going to be doing. Okay, and you actually need to do this in the tidy models framework in general as well, but it's useful just to do this up front. Next, set engine. This is a kind of strange part. Setting engine is going to say which of the computational implementations of a particular modeling strategy should the tidy models framework use when it's actually fitting these. So for example, there are many different functions in R that can fit linear regressions. LM is one of them. That's the one that we've seen, but there are others as well. And if we wanted to use one of the other ones, we could do that too. Okay, so we're not going to do that here, of course. We're just going to use the LM function. And then when we're ready to fit the data, we just say fit y tilde x, data is data. So that looks identical to our LM call before. The only difference is on this line, we're actually saying like take the model that you specified in these 2 lines and actually like compute the parameter estimates and stuff right here. Okay, when we run this, we see that the output is almost identical. So the output previously gave the call and the intercepts. Here, it is actually using that exact same call. It's just creating the call for us internally, and we don't see it directly. The coefficients that we get out, of course, are identical. So there's absolutely no difference there. Okay. Here's one of the awesome parts about using this tidy models framework, and the package that is enabling this particular part is called parsnip, is that if we wanted to change from linear regression to something else, all we need to do is change those first 2 lines. So instead, and I'll even go ahead and like copy and paste these 2 lines, there's going to be some changes here, but I think it's helpful to see kind of like how things change and which things change. So we'll go here, and if we want to do k-nearest neighbors, it'll be nearest neighbor, and you can see it's kind of templated there. We still want the mode to be regression. Sorry, I should have typed in the full term mode here. The mode to be regression, and then we need to say the number of neighbors. We'll say neighbors is 5, okay? Just kind of putting that out there. So the number of neighbors is 5. Now, you don't actually fit k-nearest neighbors with the LM function. You fit it with a function called kknn, or at least that's one of the engines you can use, and that's one of the supported engines in terms of parsnip. So we'll go ahead and use that engine, and then this line is exactly the same. So fit y tilde x, data equals data. So I'll go ahead and run this. And it says, okay, here's the call. It called train.knn from the knn package. This was the formula it used. The minimal mean squared error is 0.1661122. Okay, let's keep going. Let's say that we didn't want to fit a k-nearest neighbor model. Let's say that we want to fit a decision tree. To fit decision trees, the syntax is almost identical. We just change linear regression. Decision tree, mode is still regression. The engine that we use is rpart. By the way, don't worry about these engines. If you get them wrong, if you don't know what the engine is that runs the particular kind of regression that you want, it will suggest the possible engines that are there for you to use, okay? So we're going to use rpart to begin with, and then we will just give the fit thing again. We'll specify fit, and then the model formula, and then the data set. And here's our model object. It's a decision tree, and we can see exactly where it made the splits. So there's the root. It's at this point. If x is greater than 0.325, call it negative 0.117, and that has 14 observations in it, and so on. Okay, so this is our decision tree. If we want to fit random forest, as you might suspect, the idea is identical. So instead of decision tree, we type in rand forest. Okay, mode is still regression. The engine for random forest is called Ranger. So Ranger, and it has fit our random forest model for us. Okay, notice that the number of trees that it has used is 500. The sample size of the original data set was 21, and there's all sorts of other things in here that speak to random forest. For example, mtry is the number of variables that it would allow in each resampled data set. Well, here we only have one predictor, so it's not a particularly important quantity to look at, but for large data sets it would be, right? So that's fitting the models. What about cross-validation? If we want to do cross-validation, the idea is almost the same, and the syntax is almost the same. There is one slight difference. So the first thing that we need to do is we need to create those folds of the cross-validation set. So I'll go ahead and call that folds. So folds is vfold CV, so it could be 10-fold or 5-fold or something like that. The data set's called data, and the number of folds that I want are 10, okay? It's 10-fold cross-validation. When we run this is the kind of object that we get back. Let me clean this up a little bit so you can see it better. This is the object that we get back. So it's a tibble, and its first column has a bunch of those split objects in them, just like when we typed in initial split earlier when we were doing a single validation set. Now it's got a bunch of those in it, and they're designed in a way such that each one splits the data set into one of the folds for cross-validation, okay? Now, if we want to actually do cross-validation on each of these, we're actually going to take the code that we had before, so the linear regression, for example, right here, and the difference is going to come right here. The first difference is going to come here. I'll say fit resamples, so instead of saying just fit, I'll say fit resamples, and now I need to tell it what those resamples are. So instead of saying data is data, I'll just tell it folds right here. Okay. Now that's going to actually fit each of those linear regression models, simple linear regression models on the data set on using the cross-validation. But I only want the metrics back. So what I'll do, type in collect metrics here, and that will actually give me my estimated root mean squared error and my estimated adjusted R square. So the RMSE here, this is the quantity that I'm interested in. That's going to be my cross-validated error on the model. And then my RMSE is going to be, or sorry, the RSQ is going to be the R squared value coming out of that, which here seems very, very high, and I'm just going to disregard that for the time being. So that's how I'm going to compute my cross-validated RMSE for that kind of model. Let's try this for a different model just to see what maybe a slightly different model would look like. Still linear regression, but now it's going to be poly x. I'll use like a 6-degree polynomial. So I'll run that. The root mean squared error should be significantly less for this data set because we know that that's actually a better model. Okay, so 0.328, which is obviously a significantly better root mean squared error than the 0.647. Okay, what about other regression strategies? Well, for the other ones, we literally do exactly the same thing. Actually, let me pull the first one since it just has y tilde x. The polynomial here is kind of unique just for polynomial models. But then I'll come up here and I'll just grab, by copy and pasting, what the actual model was. So here's k nearest neighbors. And then as that's running, I'll go ahead and template the decision tree. So k nearest neighbors has, with five neighbors, has a mean RMSE of 0.386. If I do decision trees, that's here, and I can just kind of plug and play these things. So in practice, usually we would actually just save these over as like a model specification and then use that over and over again. Notice here we're getting some kind of note. A correlation computation is required, but is, there's some little issue with actually computing the R-squared value. In general, I'm not interested in the R-squared value. I'm interested in the root mean squared error, so we can actually see what that is. 0.63, if you remember, the previous ones were like 0.3, 0.386 and 0.328. So the previous models were better, and that's not surprising because we know the decision trees are actually not very good. We'll come here, and now we'll use random forest, and the random forest should be pretty good because that's a very powerful modeling strategy by using several different decision trees. So we'll go ahead and run this. The root mean squared is 0.379, which is a respectable one. It's not as good as that 6th degree polynomial, but the data looked very close to that 6th degree polynomial, so maybe that's not so surprising. The last thing that I want to show you is how to use these models to predict data into the future. Okay, and the future here is just different data sets. It's not necessarily a time-stamped future time. Okay, so to do this, we're actually going to scroll up and we're going to pull out one of our fits. So I'll just illustrate this with random forest since they all work the same way. So I'll copy my fit down here. Remember that the random forest, when you run it, will just give you that model fit. And I can type in pipe into predict, so I can pipe this directly into the predict function. My new data is, in fact, the new data set, and the model is the first object there. And then I'm going to go ahead and select the x variable just so that the predict function only sees the tibble just with the x's and not the y's. I'll run that, and I get my predictions back here for those new x's that the model had not seen when it was trained. Now, as kind of a subtle point here, the resulting object is a tibble, okay? So in the tidyverse framework, everything that comes back is going to be a tibble, okay, including predictions. So when we predicted just based on ordinary models, we would get ordinary numeric vectors back. Here we're getting tibbles, okay? So if we want to add those to a data set, we need to actually bind the columns together, okay? To do this, what we would do is we'd say piped into bind calls, okay? That will glue these two tibbles together kind of side by side, and I'll put my new data here and then dot so that it binds that new tibble next to it. So now I have my x's, my y's, and then my dot pred. In the tidyverse, it's very common to see dotted objects, meaning names of columns that have dots in front of them that signify columns that have been created by some modeling framework or something like that. So here, that's precisely what we're seeing. So we're seeing x, y, and then the y hat values so far as that model is concerned. So we could actually pipe this directly into ggplot. AES xy. My ordinary point layer is geom point, okay, just like this. We'll see that. That's not surprising, okay? And I'll go ahead and add a geom point layer where now the aesthetic of y is equal to dot pred, and maybe I'll say these should be red to see what the random forest would have predicted them to be, okay? And since these are all in line, maybe what I'll do is I'll add like a little line layer to show what the base line is, and then what the predicted line is. So I can do it just like this, line, and now we have kind of like the two curves. The black curve is the observed from the data set. That's just the predicted ones. And the y values, of course, those are the true y values. And the red curve, that is what would be predicted by random forest. So it looks a little strange in the circumstance. It's just kind of a strange data set, and the observations are kind of all over the place. But that is how you fit a random forest to a model and then make predictions with that random forest. And as you know, we could just as easily come in here and change this out for k nearest neighbors, and everything else would be the same. So just to actually illustrate that that's the case, let's go ahead and do that, just so you can see this. Here's the k nearest neighbors model. Paste this in here, run it, and we can see this is what the k nearest neighbors prediction would look like. So it's a really nice, consistent, and extensible framework. The Tidy Models framework is for fitting models, assessing them, and making predictions on data that the models have not yet seen.